Our last section talks about real numbers, but more importantly, it's going to end up talking about something called modular arithmetic. So we spent all this time with these different classifications: natural numbers, whole numbers, integers, rational numbers, irrational numbers. Now we can get to real numbers, which is really everything you've been working with. So real numbers is given by that R. And the way we're going to define this is with that set builder notation. So we say X is a real number as long as X is irrational or rational. So every real number is going to be classified as one of those two things. So with this example, we're given a list of numbers and we want to pick out what are the natural numbers, what are the whole numbers, the integers, the rationals, the irrationals, and the reals. And really, in order to do this, I do need to simplify some of these. So if I look at -3/4, you plug that into your calculator, you would see that's -0.75, just so you have an idea. This bar on top, again, is going to indicate that the 6 repeats. Here, if you plug √5 into your calculator, it is not going to be a nice number. But however, square root of 81 we can do. That is going to be 9. So when I'm looking for natural numbers, those are going to be the nice counting numbers excluding 0. So this is not a natural number, not natural. Also not a natural number. No, no. This is the only one that results in a natural number. So the natural numbers is just the square root of 81. I have to write it as it was listed. Moving on to my whole numbers from this grouping. Well, all of my natural numbers are whole numbers, and that's going to also include the number 0. So 0 and √81 are my whole numbers. Bumping it up to integers, all of these are integers as well, but now we can include negative values. So I can throw -7 into this list. So these are my 3 integers. Now going on to rational, that's going to be the integer over the integer. So it's going to be terminating or repeating decimals. And again, every single integer is a rational number. So I'm seeing, are there others added in? Well, this is going to be a rational number. It's an integer over an integer. And so is this, since it's a repeating decimal. So really, it's all of these numbers with -3/4 and with 0.6 repeating added in. My only irrational number is going to be that square root that does not simplify. So that is the square root of 5. And then my real numbers are really every single one of these. You merge these to the one single list, but again, every single one of these numbers can be classified as rational or irrational. So really, this is all of the numbers. So I'm not going to bother writing every single one. That is just the entire list, okay? So what we're going to talk about really for the majority of this section is going to be this modular arithmetic. And so to introduce the idea, we're going to talk about something that's called symmetry and clock addition. So a symmetry of an object is a motion that moves the object back onto itself. So basically this means at the end of the motion, you'll never be able to know that the object was moved or that the operation really ended up happening. And so the way we're actually going to talk about this is through clocks, but you can think of it also by flowers. So this is just an example of a nice little flower here, but this one has 6 petals that are all the same size. So if I go ahead and I rotate this petal around, you're really never going to be able to know that it was ultimately moved because it'll land in exactly the same spot. So this particular flower has 6-fold rotational symmetry. And again, this creates what's called a clock addition. So it's still like our addition, but we put it inside a circle to indicate that it's a clock. Okay, so basically you can consider all of these petals to have a number. It's 6 petals, but really we're always going to start at 0. So that's petal 0, petal 1, 2, 3, 4, and 5. So I can create a clock from this with 0 at the start, 1, 2, 3, 4, and 5. And then we've got the center of our clock. So what I'm doing is if I'm adding 2 of these values together, it's still going to land me at one of these 6 numbers on my clock. So my result is always going to be a number between 0 and 5. So again, 6 petals, the biggest possibility you're going to have is 5. So we're going to do a couple examples with this, and then we'll end up creating a chart for our clock addition. So you can see in the 6-fold, here are the 6 values, and we're going to see if we add them together. So basically this entry would be 0 plus 0 under the clock addition. This entry here would be 3 plus 1 under clock addition. So just to get some practice, we'll start with 2 plus 3. So essentially assume your hand starts at the 2 and you're going to add 3. That basically means you're gonna start at 2 and you're gonna go 1, 2, 3 petals over. So the result will be 5. Okay. If I do 4 plus 5, well, you could think in your head that's 9, but that's not one of the values in our clock. Okay. It's kind of like when it's 7 o'clock and you're thinking about 8 hours later. 7 plus 8 is 15. That's not an hour time. So you have to actually go ahead and remove the 12 from it to land you back at 3 p.m. or whatever it is. So if I start here, my hand is at the 4, and now I'm going to go forward 5 hours. So 1, 2, 3, 4, 5. So this lands me at 3 on my chart. If I do 3 plus 4, again, I'm starting at 3. And then I'm going to go forward 1, 2, 3, 4. So this lands me at the 1 hour. Okay. So again, if you think about 3 plus 4, that's 7. But again, that's bigger than 6. So if I take away 6, it leaves me at 1. 4 plus 5 gives me 9. Again, bigger. So I remove 6 from it. It lands me at 3. So again, you can do these operations. We're going to utilize this chart for the first couple problems. But if you think here, basically in this first row, I'm going to take 0 and I'm going to add all of these hours to it. And that's like best case scenario, because you add 1, you're at 1. Add 2, you're at 2. Add 3, you're at 3. 4, you're at 4. 5, you're at 5. So if you start at 0 and add nothing, lands you at 0. 0 plus 1 is 1. 0 plus 2 is 2. 0 plus 3 is 3. 0 plus 4 is 4. And 0 plus 5 is 5. Okay. And then really you're going to do the same thing for each of these charts. I'm going to start at 1 and I'm going to add all of these values. So if I start at 1 and add nothing, it still leaves me at hour 1. 1 o'clock plus 1 o'clock, or 1 hour, lands me at 2. 1 o'clock plus 2 hours lands me at 3 o'clock. 1 o'clock plus 3 hours is 4. 1 o'clock plus 4 is 5. And then here, when you do 1 plus 5, that lands me at 6. Problem is, that's not one of my hours. So if I'm starting at 1 and I'm going forward 1, 2, 3, 4, 5, that lands me back at 0. So if you notice, all of these result in the numbers 0 through 5. So it's going to appear once in each of these columns. Now if I move on to 2, well, 2 plus no time still leaves me at 2. 2 plus 1 hour is at 3. 2 plus 2 hours is 4. 2 plus 3 hours is 5. Now if I do 2 plus 4 hours, that lands me at 6, and 6 is really the same as 0. And then 2 plus 5 hours lands me at 7, but again, if I'm starting at 2 and going forward 5, 1, 2, 3, 4, 5, that lands me at 1. So really, maybe you can kind of notice a pattern. What happens is all of these numbers get shifted down, and the one at the end moves. So this was shifted down 1, shifted 1, shifted 1, shifted 1, shifted 1, and then the start got moved to the end. Same thing for the next one, shifted, shifted, shifted 1, shifted 1, shifted 1, and then moved to the end. And really this pattern's gonna keep happening, so really what you end up with is a diagonal that is always going to be the same value. So this next row, I really don't need to go through. I'm just gonna go ahead and move everything down 1. So this is 3, 4, 5. Now you go back 0, 1, 2. Okay, so everything got moved. Shifted again, this one starts at 4. So 4, 5. Then I restart 0, 1, 2, 3. And then finally shifted again, that gives me 5. Then 0, 1, 2, 3, 4. So again, you get really, really, really nice patterns, okay? There's a lot of symmetry that goes on because if you think back up to here, if you did 2 and then you added 3 to it, it lands you here. But if you also started at 3 and went to 2, it lands you at the same spot. So these are actually some properties that you're gonna go over, but there's symmetry. So if I do 2 plus 3, it lands me at 5. But also if I do 3 plus 2, it lands me at 5. So you get a lot of different symmetry within here. So when we have new systems like this, we really have a bunch of different properties that end up coming into play. And so we're gonna go over those different properties here. So first, we've got the closure property. And what that states is if you take the sum of any two numbers, it's going to result in a number that belongs to that set. So basically here for my clock addition for 6-fold symmetry, your values are the numbers 0 through 5. No matter what, when I do that addition, my results are the numbers 0 through 5, nothing else. For the commutative property, the order is not going to matter when you switch it. So basically 1 plus 2 is the same as 2 plus 1. So with clock addition, if I add two values together, the order does not matter. It's exactly that symmetry. The associative property basically is a way that you can regroup parentheses. So if I want to do these two operations together, really I'm going to be able to move those set of parentheses around. So instead of doing A plus B first, I can do B plus C first. Then likewise, if I have the distributive property, or it needs to have the distributive property, that's exactly like when we distribute when we're solving equations. So really, I can distribute this to the first one, and I can distribute it to the second one. So I can do instead A plus B first, and then A plus C as well, and then go ahead and add these results together. Then for any system, we also need two different things. We need something called the identity and something called the inverse. So the identity is going to be one set value. So basically, if I take a number and I add this identity I, it's going to do absolutely nothing. It keeps the element the same. If you think of real numbers, the identity is 0. Anytime you add 0, it does nothing. So this I is called the identity element. And there is a single identity for the entire system. Okay. For inverse, it's going to be specific for each number. So basically what happens if I take A and I add its inverse element, it's going to land me back at the identity. So again, I is still the identity, but V is the inverse element of just A. So every single element is going to have its own inverse. So if you think about real numbers, again, your identity element is 0. So if I take 5, its inverse element would be -5, because when I add them together, it ends me at 0. The inverse of 17 is -17. So every single one is unique. So for this 6 clock symmetry, we're going to just verify a couple different things. We're going to make sure all of these are in here. So starting with the closure property, what I want to make sure is that I don't have anything outside the elements 0 through 5. These are the numbers on my clock or my pedals. They should be the only things in my chart, and indeed they are. So the closure property is verified by saying all the elements in the table are the numbers 0 through 5. You get nothing outside of those digits on the clock. To verify the associative property, we're going to verify that if I do this addition, it's the same as if I go ahead and I move my parentheses over. So I'll do the 3 plus 4 first. So this is the one time we are verifying this. I'm going to go ahead and just work on both sides here and make sure I end up with exactly the same thing. So we can use our chart to our advantage. You don't need to go through these again. But 2 plus 3, that lands me at 5. But going through my chart, I look at 2, I look at 3, and I go to where they meet. 2 plus 3 gives me 5. So this results in 5 plus 4. And again, 5 plus 4 is 9. That's more than what we have. So you can remove the 6 from it, and this should be 3. But going to my chart, I look at 5, I look at 4, and I see where they meet. And that element is going to be 3. So this ends up equaling 3 on this side. Now I want to see if I go through and do this order instead, do I still land at 3? So starting inside my parentheses, looking at 3 plus 4, and tracing that over, it lands me at 1. So this side gives me 2 plus 1. And again, looking at 2 and 1, that goes ahead and gives me 3. So indeed, these end up giving you the same result when you switch that order. Okay. For the identity, what I'm looking for is which number do I add that does not change the result. And really, we're going to look at both of these. If you notice here, the exact value is directly underneath. So when I take 1 and add 0, lands me at 1. 2 plus 0 is 2. 3 plus 0 is 3. 4 plus 0 is 4. And 5 plus 0 is 5. So 0 is our identity element. Okay. Just to show you, if you take 0 and you add 0, oops, put my equal sign too soon, lands you at 0. If I take 1 and I add 0, lands me at 1. 2 and I go forward no time is 2. 3 and I go forward no time is 3. 4 plus 0 is again 4. And 5 plus 0 is 5. Okay. So anytime I add 0, it does not change anything. Moving on then, the last thing we're going to do is the inverse property. So I'm going to have to go back up to the chart in a second. But basically I want to see for each of these numbers, what do I add to land me back at 0? Should always be 0. Okay. So starting with the first one, I'm going to go to my 0 column and I want to see which number do I add that lands me at 0. And really that's just 0. So 0 plus 0 gives me 0. So 0 is the inverse of 0, kind of a weird statement. Okay? Let's use this in a different color. Then I want to look, if I go to 1, I want to see what number results in 0 when I add to it. And that's going to be 5. So the inverse of 1 is 5. And really, that ends up telling me the end, because remember, the order doesn't matter. The inverse of 5 is going to be 1. So that lands you at 6, which is that starting time. Moving on to 2, I want to go see where does it equal 0. And that tells me when I add 4. So 4 is going to be the inverse of 2. And likewise, 2 is the inverse of 4, because these add together to give me nothing. Then last up, we've got 3. And so tracing this over, here's the value that I have to add that lands me back at 0. And so the inverse of 3 is 3. Okay. So this is our introduction to what is known as modular arithmetic. This is really the most important part that we need to take away. Okay. So modular arithmetic is just like clock arithmetic. You're always going to end up with a number in that set. Instead of doing like a 6-petal flower, we might have a 12-petal, a 9-petal, a 7-petal. It can be any type of clock that I want. So I'm going to start by introducing what we end up writing or what we end up saying. So we say A is congruent to the number B modulo M, which is written as A triple equal sign B mod M. You might also see this in parentheses. This is called our modular class though. But the way these are going to be congruent is if they end up having the same remainder when you divide by M, okay? So I'm going to show you an example with this, but you're definitely going to need a calculator for some of this stuff. We're going to do division by hand, but you are going to probably still need a calculator for that. So if I think about 3 divided by 7, you could try to plug that into your calculator, but 7 does not go into 3. This equals 0, and there is a remainder of 3 to it. So just to refresh you on long division, you're taking the number 3, you're dividing it by 7. This number does not go into 3, so that means we put a 0 above it. Then we go ahead and we multiply these two pieces, and 0 times 7 gives me 0. And then I subtract it, and so I'm left with 3, and that is my remainder. Okay. If I take 10 and divide it by 7, you'll see it's 1 point something. Just to show you with long division, 7 goes in, well, it doesn't go into 0, but it does go into 10 one time. Then multiplying these two, 7 times 1 gives me 7. And we subtract it, and that gives us that remainder of 3. And we stop because this number is less than what we're dividing by. So 10 divided by 7 is equal to 1 with a remainder of 3. So these both have the same remainder when we divide it by 7. So what that tells us is the numbers 10 and 3 are equivalent to each other under the modulo class of 7. So 10 is triple equal to 3 mod 7. Okay? Because they both have the same remainder. Right? So ultimately, if our modulo class is 7, then we write A is equal to whatever, mod 7. No matter what you divide this by, it's going to be the remainder. So it will always equal one of the numbers 0, 1, 2, 3, 4, 5, or 6. You will never get 7 because 7 is divisible by 7. The remainder is always going to be a number 0 through 6. So it is just like that cloth arithmetic. When you had six-fold symmetry, the result was always a number 0 through 5. If my modulo class is 15, the only possible remainders are 0 through 14. So it's always going to be one less. So what we're going to do is we're just going to do a bunch of examples where we're going to have to fill in the blank. So we're going to start with, what is 9 equivalent to under modulo 3? So again, I'm looking for the remainder. This answer should be one of the numbers 0, 1, or 2. Those are the only possible remainders, okay? So I need to do long division. I need to take 9, and I need to divide it by the modulo class, which is 3. And thankfully that does go in nicely. 9 divided by 3 gives me 3. So if I multiply 3 times 3, it gives me 9. And my result is 0. So 9 is equivalent to 0 mod 3. Okay? So just to write this out, 9 divided by 3 is 3 with a remainder of 0. So 9 is equivalent to 0 mod 3. Okay. Moving on to a bigger number, we're going to try 412. What is that equal to under the modulo class of 7? And again, my answer should be a number 0 up to the number 6. Okay. So I've got to go through and I've got to do long division of this. So I want to take 412 and I want to divide it by 7. So looking at the first number, 7 does not go into 4. So if you need to, you can put a 0 here, and then that would be 0. You bring the next number down, but really just look at the 41. That's the first thing 7 goes into, and really it's going to divide into that 5 times. So there's a couple different ways you can do this. You can take it piece by piece. So starting with 4, that does not divide by 7. I don't get a nice number. If I do 41, the next 2 digits divided by 7, I do end up with something nice, but you see you have that remainder. So 41, or 7 goes into 41 5 times, okay? So again, what I do is I go ahead and multiply the 7 and 5, and that leaves me with 35. When I subtract it from those 2 digits, that leaves me with 6. And then I bring the next number down, which is 62. Okay. Now I want to see how many times does 7 go into 62. So if I divide that, you get 8 point something. So that tells me it definitely goes in 8 times. And again, repeat the process. If we do 7 times 8, that's 56. And then if I subtract that, my remainder is 6, okay? So ultimately, I stop here because my remainder is less than what I'm dividing by. So if I take 412 and I divide it by 7, it ultimately goes in 58 times, and I have a remainder of 6. So that tells me 412 is equivalent to 6 mod 7. Now, realistically, you don't need to go through, again, every little detail like this. What you can also do, just to show you off to the side, if I take 412 and I divide it by 7, and I scroll over, you see it goes in 58 times, and then there's stuff left over. So I can put a 58 up here. Now I can do 58 times 7 to see what that equals, and that gives me 406. So I put a 406 underneath, and when I subtract those two, 412 minus 406 indeed results in the same remainder, okay? So let's try some more examples. We've got 6 is equivalent to what? Mod 4. So again, I'm starting with 6, and I want to divide it by 4. And really, that just goes in a single time. And hopefully this one's not too terrible. 1 times 4 is 1. So I'm left with a 2. So 6 divided by 4 leaves you with 1, and you have a remainder of 2. So my result is 6 is equivalent to 2 mod 4. So really what ends up happening is you're basically taking this number and you keep subtracting 7 until you land at a number between 1 through 6. Likewise here, I take 6 and I subtract 4 until I land at a number between 0, 1, 2, or 3. So 6 minus 4 gives me 2, and that is in those possible results, okay? For this next one, well, I've got some addition over here, so really I need to go through that first. What this is really asking then, 6 plus 4 is 10, so 10 is equivalent to what under mod 4? Okay. So going through that division, we're gonna take 10, and we're gonna divide it by 4. If I do that, you end up with 2.5. So it goes in 2 times for sure. We need to see what the remainder is. So 4 times 2 gives me 8. When I subtract that, the result is 2. So my remainder is 2. So really in both of these places, I can add 2. And if you notice, between these two examples, when I added that modulo class, it didn't end up actually changing the results. So 6 is equivalent to 2 mod 4. When I then add 4 to this side, it does absolutely nothing. So this is really beneficial when you end up with negative numbers over here. And that's going to be our next example. If I have 3 minus 4 and I want to find what that's equivalent to under mod 3, again, remember my results should be a number either 0, 1, or 2. Stops at the 1 right before it, okay? So 3 minus 4 gives me negative 1. So this is asking negative 1 is equivalent to what under mod 3? So I can't quite do that. If I take negative 1 and I divide it by 3, you end up with nothing. So how do you deal with a remainder with a negative value? This is exactly where we're going to keep adding the modulo class until I end up with something nice. So here we're going to add the modulo class. Because it's really the same, 3 minus 4, if I add 3 to it, it does not change the result at all. So again, you're really adding 3, okay? So this gives me 2 is equivalent to what under mod 3? And that's something I can actually figure out. So if I take 2 and I divide it by 3, well, that gives me 0. It goes in no times. So 0 times 3 is 0. Subtracting the 2 results in 2. So my remainder is 2. So really 3 minus 4 is equivalent to 2 under modulo 3. I can fill in 2 at all of these places. But really this is what you started with. 3 minus 4 is equal to what, mod 3? And that answer is going to be 2, okay? So I really have one last example for you, and it's gonna be something that relates to our calendar. So if you think about our calendar, every single 7 days repeats on cycle. So Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Then it starts back up. Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Likewise with months. You have a cycle of 12 months that continues over and over and over again. So we're really just going to do one last example utilizing that calendar. So if today is Friday, we want to figure out what day of the week will it be in 82 days. So writing our calendar days out, just using a letter, we've got Sunday, Monday, Tuesday, Wednesday, Thursday, I'm going to use an R to distinguish, Friday, and then Saturday. So ultimately I have 7 days in a week. So the week is modulus class 7. So essentially every single week that passes will still land me at Friday. So ultimately I just need to know what is my remainder, and then I'm gonna go forward that many days. So ultimately I need to figure out 82 is equivalent to what under mod class 7. So going through our division, I want to take 82 and I want to divide it by 7. And then I'm going to trust you can do this at this point. If you take 82 and divide it by 7, it will give you 11 point something. So going through 11 times 7 gives you 77. Subtracting the 2 results in 5, and that number is less than 7. So 82 is equivalent to 5 under mod class 7. Okay. So basically, I'm going to have 11 weeks that pass. That lands me at Friday, and then 5 more days after that. So I need to figure what is 5 days from Friday. So going through, let's go ahead and just copy and paste my days of the week down. So I'm starting at Friday and I'm going forward 5 days. So that's 1, 2, 3, 4, 5. That lands me at Wednesday. So 82 days from Friday will be a Wednesday. So again, you can do exactly the same thing with months. It's just a different modulo class of 12, because there are 12 months. So if you need to figure out if today or this month is April, in 97 months, what month will it be? You go ahead and just do division with modulo class 12 instead.